So what I would like to present to you today is our approaches, how we deal with toxicology or how we deal with toxicity. Being someone who is coming from medicinal chemistry, so I was trained as a medicinal chemist and did my PhD pure synthesis and then gradually moved to the computational part and now run a group on pharmacoinformatics here in Vienna. So how can we contribute to one of the most, let's say, pressing problems we still have? You know that the main reason for attrition is lack of efficacy, but the second main reason for attrition in the drug development process is toxicity. And here you see that was a paper from Nature Reviews Drug Discovery, that you see here the let's say how many compounds you need per stage and to come through, and you see in each individual stage, unfortunately for whatever reason my mouse is stuck, you see for every stage how many compounds you need and what the costs are, and you see preclinical development $150 million, phase 1 270, phase 3 319, so it's roughly more than $500 million out of the 2, 3, 4 billion you need, which is caused basically by toxicity problems you overlooked in the very, very early discovery phase. And as a computational chemist, what can we do in this respect to maybe overcome these problems or to very, very early detect potential toxicity problems? And I would say basically we have here mainly two possibilities. One is a data-driven approach and one is a modeling approach, a modeling-based approach. And when I talk about modeling, of course, we have all the tools we have available. So 2D QSAR, 3D QSAR, pharmacophore modeling, docking, machine learning, deep learning. And when we look on the, let's say, knowledge-based approach, that actually means we have a compound, we know how the compound interacts with the target, we know how the target interacts in the pathway or is embedded in the pathway, and we know how this pathway is somehow related to a disease. I guess we have several options. And today, what I would like to present is basically three main options we are using here. One is trying to predict the compound target interaction, knowing that the target is related to toxicity. The second approach is, can we directly predict how a compound influences a disease or a toxic side effect? So that's more on the machine learning, deep learning side. And finally, at the end, I would like to show you our first attempts, how we can predict or let's say analyze how a compound interacts with a certain pathway, so that we get a sort of a compound pathway interaction fingerprints. So when I'm talking about targets, I guess you know the first one, the most important, let's say the first one which always is coming into our mind is the hERG potassium channel, where you have a more or less clear link. If a compound blocks the hERG potassium channel, it's prone to arrhythmogenic potential. We have certain IC50 values where we consider compounds being safe or being unsafe, but there are a lot of other proteins when your compound interact with, you should be careful. And our, let's say, main playground here are transporters. I started already in my PhD, I synthesized compounds. At that time, it was sodium channel blockers. And right after my PhD thesis, we discovered that these compounds are also interacting with P-glycoprotein. And P-glycoprotein, most of you might know, is an efflux transporter, is one of the 48 ABC transporters we have in our genome. So it's just pumping out compounds from inside the cell to the outside of the cell, and thus giving rise to drug resistance in tumor therapy, or also influencing finally the ADMET profile of a compound. It might be also related to toxicity. When you think about neurotoxicity, in that case, it would be quite helpful to have active PGP and to have compounds which are transported by P-glycoprotein, because then they don't even enter the brain. So we have for the ADMET transporters in our genome, where for most of them we know quite well what they are doing. Just on the right side, you see here different organs like the intestine, the hepatocytes, the blood-brain barrier, the kidney, and you see the inward and outward transporters, or the main inward and outward transporters, which are expressed here on the respective barriers. Where we know much less from is the SLC transporters. We have around 460 SLC transporters in our genome. They are mainly inward transporters, so they are pumping compounds in, and they are also related to toxicity. For example, when you just look on the hepatobiliary circle, we have NTCP, which is pumping in bile acids from the blood to the hepatocyte. It's an SLC transporter. We have BSEP, the bile salt export pump, which is pumping the bile acids to the bile duct. And we have ASBT, which is in the intestine, pumping the bile acids back from the intestine to the blood flow. So that you have 3 transporters, 2 SLC transporters and 1 ABC transporter, and all of them are required for keeping bile acid homeostasis. And we know that bile acids in principle are toxic. So when you have accumulation of bile acids, for example, in the hepatocyte, which might be due to BSEP being blocked, then you run into cholestasis as one of the main liver toxicity side effects we might observe. And this is one of the reasons, for example, why FDA asks for a set of transporters which should be tested, need to be tested when it comes to registering a drug. And some of them are ABC transporters like P-glycoprotein or the breast cancer resistance protein. Others are SLC transporters like OATP, OCT, or OAT1. So when we target transporters, we started very conventional with QSAR models, so getting correlations between physicochemical properties and biological activity. In that case, we were working on inhibitors of P-glycoprotein. So on the left side, you see the simple correlation lines, which finally don't really tell us a lot, because we know that the access to the protein takes place via the membrane interface. So having a nice correlation with lipophilicity should be something we expect. But when you compare the blue line with the red line, you see all those compounds having this distinct modification on the nitrogen, this hydroxyphenyl piperidine group. All of them show a factor of 10, because it's a logarithmic scale on the activity axis, show a factor of 10 higher activity than expected based on their lipophilicity. So this is something, when you look on the correlations, you then should analyze, because these are the outliers. This is something what tells you more than just you have a correlation with lipophilicity. And we used, for example, this information to finally validate our docking poses when we went into structure-based design with this protein. And here you see one of the compounds docked into P-glycoprotein, into the very huge binding site. It's 8,000 cubic angstrom, so it's 10 times larger than a normal, let's say, standard binding site. And what you can see here on the upper side, it's really interesting that, sorry that my mouse simply doesn't work. What you see on the upper side is that you see the interaction of this hydroxy group with the tyrosine 310. So what we do here, we call that experimental data guided docking. So we just don't rely on scoring functions. We dock the compounds in, we just enumerate the, let's say, pose space we can get, the top 100 poses ranked by a set of scoring functions. Then we cluster them according to the common scaffold, different compounds, and then we analyze if the docking pose or if the respective cluster allows us to interpret the SAR we see. And we know the hydroxy group from the phenyl hydroxypiperidine moiety is important. Otherwise, we wouldn't see this effect in the conventional Henge analysis in the 2D QSAR. So we know that we need the hydroxy group. We know that we do not need the hydroxy group of the ethanol propanolamine side chain, and there is also not an interaction. And we know that we need the carbonyl group, and you see very good here on the pose. There's an interaction with tyrosine 310 to the OH group of the hydroxyphenylpiperidine. There is an interaction with the tyrosine 307 with the carbonyl group, and there's no interaction with the hydroxy group of the. Now the mouse works very good. I get some information from Steve from Marcus, cool. And no, it no longer works again. And this allows us to finally prioritize a docking pose and go a step further. And the question is, how can we validate docking poses like that? And what we actually do here is we type mutations. So of course, obvious, when you look on the docking pose and you say, okay, let's mutate the tyrosine to phenylalanine, both tyrosines to phenylalanine, you should expect a decrease in affinity. Unfortunately, in this very promiscuous, very also flexible transporters, it's not that trivial. We have two entry sites. On one side, we have these two tyrosines. On the other side, we have 6 tyrosines. So finally, when we did the mutations, nothing happened. So what we normally, and what we now in a more or less standardized way are doing, is we transfer the docking pose, the validated pose, which allows us to explain SAR, to a structure-based pharmacophore model, and we use the structure-based pharmacophore model to do screening of a library, order then the top-ranked hits, buy them, and test them. So that's one way of doing the validation, so really doing the prospective, predictive validation. And in the second, here on the right side, you see that's another way of doing the validation. In that case, we just then used the docking protocol, which finally gave predictive results, and just docked 2,000 compounds into P-glycoprotein, taking the top scored pose for each compound. And when you plot, then here you see the scoring values against, you do a histogram plot, a frequency plot. You see here are the inhibitors and here are the non-inhibitors. And when you just take the intersection here and use it on a threshold and use it as a classifier, so that's a sort of a structure-based classification for P-glycoprotein inhibitors, you get a 75% accuracy, which finally is not that bad, considering that it's a structure-based, in that case done on a homology model of a flexible transporter. We also did stuff like that for the bile salt export pump for BSEP. Here we used a data set from AstraZeneca, and this is also something I would like to stress out here. When we look on all the transporter models we have, then finally the best one, on my feeling, when it comes to validation, is the one built on the in-house data set of AstraZeneca, around 100,000 compounds. It's one assay, it's internally QC'd, so that's a quite robust random forest model. And what we further did after having constructed this sort of machine learning models, inhibitor, yes, no, we screened drug bank, we identified bromocriptine as one of the potential inhibitors. We tested it and confirmed experimentally that indeed bromocriptine is also inhibiting the bile salt export pump, which before we did the study was not known. Also here in this study, we did then the large scale docking, and here we went a step further. What you see here is critical amino acids in the protein. So you see a heat map, partial structures, fragments of the individual compounds, and the interaction with certain amino acids in the bile salt export pump. So this allows us to identify a set of hotspots, which sort of partial structure, structural moiety is mainly interacting with which amino acid, and also identify amino acids which might be important for interaction. Because of course, one of the main things we are always asked, what should we do to, for example, avoid the PGP interaction or to avoid BSEP interaction? Just to set the expectations right, it's still for us quite, we can't really tell you. In case of PGP, I would say, okay, put a negative charge in because we know that the protein doesn't like negative charges, but more is still a bit complicated. So that's a study on the OATPs, on the bilirubin transporters, which finally, if there's some interaction with these transporters, the compounds might cause hyperbilirubinemia, another liver toxic side effect. So what we did here is we also compiled a large data set from literature. It's more than 2,000 compounds. We made 3 different machine learning models per transporter, so OATP1B1 and OATP1B3. We screened drug bank, used a sort of a consensus scoring of the different machine learning models, and also bought the compounds and tested them. And here you see something which we, to be honest, very rarely see, that 7 out of 10 compounds we bought indeed were active on the OATPs. Normally we have here a positive hit rate of about 20% when we use machine learning, for example, for screening drug bank, buying compounds and testing them. The question now is, you might wonder, how is this related to toxicity? And this I would like to show you on the next slide, because having now validated transporter models, having predictive transporter models, you can combine them with classical machine learning models. What does this mean? We had a data set, we just collected a data set for drug-induced liver injury for DILI, around 1,000 compounds, half of them are a bit more DILI positive, half of them DILI negative, or let's say less than half of them DILI positive and a lot of them DILI negative. That's generally one of the problems we face in toxicity. We have quite unbalanced data sets where classical machine learning sometimes really comes to its limits. And what we did then, we did classical machine learning model, yes, no, DILI positive, DILI negative, but we included our predicted hepatic transporter interaction profiles. So we have models for PGP, for BCRP, for BSEP, OATP1B1, OATP1B3. We have also models for substrates for these transporters. And so we predicted a sort of a transporter interaction profile for each compound and used it as additional information, as additional descriptor in the DILI, hyperbilirubinemia, and cholestasis machine learning model. So we combined classical physicochemical descriptors, for example, from Aldikit or from MOE, with predicted transport interaction profiles. And here you see the results. You can read the individual results up in these 3 publications from Eleni. She's currently now at GSK in the computational toxicology. And what you see, it's depending on the side effect. If you get, let's say, a more robust model, if you include predicted transport interaction profiles, in DILI it simply didn't work. But DILI is extremely complex and it has a lot of different causes. And so there is adding transporter inhibition information doesn't increase the performance of a DILI model. In hyperbilirubinemia, it worked so in between. The model with respect to its statistics wasn't better than just taking a set of descriptors and making a hyperbilirubinemia model. But the transporters, when we did random forest and we did a variable importance analysis, the transporters were ranked very high. In cholestasis, when we made a cholestasis model, we saw that finally the model substantially got better, so it showed a better statistics. So including predicted transport interaction profiles just increased the model's performance. Interesting, it was not just BSEP, so the bile salt export pump, which we would have expected. We needed the whole panel of transporters, the whole interaction fingerprint to get a substantially increased performance of the cholestasis model. to just not have this somehow documented in publications, we provide these models. So here you see the transporters and the toxicity prediction models as a web service on our website from the university. So it's just you go to livertox.univ.ac.at, you draw a structure, and you get the predicted interaction profile. We have here a score between 0 and 1. The threshold is 0.5. So less than 0.5, we consider the compound inactive. More than 0.5, we consider it as active. And of course, seeing the values, for example, here for MRP2 transport, if it's 0.4, I would be a bit more critical in comparison having 1 or having 0. So these are the stronger signals. These are, I guess, the less strong signals. So these are the transporter models we provide for free at the university website. As Marcus pointed out on the introduction, 1 year ago, together with 2 colleagues of mine, we founded Phenaris. Phenaris is basically a company focusing on also doing toxicity prediction and transporter modeling. In case of Phenaris, if you go to transport.phenaris.com, we have currently 4 ABC transporter and 2 SLC transporter implemented. In that case, we offer a pay-per-use model, or finally, you also can get a Docker image and have the models in-house. So I just show you a few screenshots. What's the difference to the free models? It's not only one algorithm, one classification algorithm, it's 3 different classification algorithms. So for every transporter, we have support vector classification, random forest classifier, and the k-nearest neighbor classifier. It's actually interactively, so you draw a compound, you get the profile, you modify the compound, you get the profile from the modified compound, and so on. We also offer here applicability domain, which is based on the density, on the environment of each individual compound and the density of the environment. You can download the results, and you also can do a batch execution and just upload an SDF file. So how does this look like? Here you see, for example, for bepretil, you see the interaction profile here. I just marked all transporters. You can do the modifications. You just go back, exchange this nitrogen by carbon, as I did here, and you get the next profile, exchanging this nitrogen also by carbon. You get the next profile. You see the models are sometimes in agreement, but not always. So this is why we offer 3 different algorithms and allow the user finally to decide, because when you have your in-house compounds, maybe some of a certain classifier works best for your chemical space and for your compounds. With respect, and here you see also what I said on the beginning, when I changed this part here to a carboxylic acid, you see how PGP inhibitory activity goes down. So you can just really follow what a distinct modification, the effect of a distinct modification on the prediction for the respective transporter. So for a medicinal chemist, you can a bit play around and see what could be possible modifications and how would this result in the predicted transport interaction profile of my compound. Here you see the applicability domain assessment. For every transporter, you get in or out of domain. It's for every transporter, not for every model, because finally it's depending on the data set per se. And we of course always use the same data set for one transporter. And here you see the graphical visualization, how close it is in the domain, or maybe might then later on be out of domain. So this is how we also offer commercially transporter models for either the web-based pay-per-use that's installed on the Amazon cloud, or getting a Docker image and using it in-house. Combining now these approaches, let's say machine learning and structure-based approach we did in EU tox risk for the respiratory complex 1. What you see here is the work of Jennifer and Florentina. So we combined here, we did a docking of degoylin and rotenone, because in EU tox risk it's about chemicals and predicting, doing a let's say, read across, trying to avoid animal experiment based on in vitro and in silico tools, so new approach methods. We took dequelin and rotenone into respiratory complex 1, constructed a structure-based pharmacophore model, used it for screening of a compound library. In parallel, we did a machine learning of, we had compiled a data set of around 6,000 compounds where we knew they show mitochondrial toxicity or not. Did machine learning model combined, used also the machine learning model for screening, combined the hit lists, ordered 10 compounds or 20 compounds, tested them, and indeed identified 2 compounds which showed considerable respiratory complex inhibitory potential. So this is combining, let's say, machine learning with structure-based design to not only getting a model, but also getting on the structural basis insights, what are the crucial interaction parts for maybe causing this sort of toxicity. I mentioned on the beginning that most of our data sets suffer from being imbalanced, and the more imbalanced they are, the more problematic classical machine learning gets. And in addition, of course, we also wanted to somehow go into deep learning because it's a hype. I'm not saying that our problems will be solved with deep learning. On my feeling, in a few years from now, it will be a method established as all the other methods, as classical machine learning, as pharmacophore modeling. It will be one of the tools we are using when we have a certain setting in our data. In that case, I guess the importance is having large data sets, which we normally don't have in our domain, and then having complex problems. Toxicity definitely is a complex problem, look on DILI, but we don't have large data sets. And what do you do in classical machine learning if you have high imbalance? You do, for example, SMOTE, or so you just increase your positive, your minority class with somehow artificial instances, or you just do bagging, you reduce the majority class and do it several times. So our approach is here somewhat different. We thought we can just solve both problems, so the imbalance and the low number of objects with just one stone, so 2 birds with 1 stone, or 2 flies with 1 trap, as we would say in Europe, by not using artificial instances, but using real instances in a way that in Cover, this just went online a few days ago, is what we do here is we use 3D descriptors. We use conformation dependent 3D descriptors like Wolfsref, and just take a compound, enumerate 100 conformations, and use 3D dependent descriptors. So basically each conformation is its own object, has its own entry, and that's then very simple to balance because, for example, from the majority class, you just sample 5 conformations. From the minority class, you sample 50 conformations. And if you have 10 to 1, you are suddenly 1 to 1. The method on the beginning, it wasn't made to make better models. It was, we had quite some discussion with the referees here, but we see that as an additional possibility to cope with the problem of imbalance and low number. And the performance was as good as when we do classical machine learning. It was not better, to be honest, but it was not the aim of this first study of Jennifer to make better models. It was showing that it works. We did not optimize conformation generation. We did not optimize descriptors. We just used standard conformation enumeration in our kit, and we used standard 3D descriptors. Another possibility, which so you can read that up, the comparison to 1 to 1, 1 to 5 upsampling, 1 to 10. So it's a data augmentation approach. Another data augmentation approach is I had a postdoc actually, and she was very interested in doing image recognition also in arts, for example. She comes from physics and now is in CERN. And what we tried there is, why not using directly pictures? Why going, let's say, the long way, having a structure, doing descriptors, then using descriptors. All of you know, when you look on a structure with a certain experience, you get a feeling what this compound might do or might not do. So in that case, we more or less use the same approach. We made a 3D enumeration of the compounds, and then we made pictures from different angles and then use classical image recognition. Also in that case, the method basically is from scratch as good as when you do classical machine learning methods. And of course, also you can do that for increasing the size of your data set. You can do that for balancing imbalanced data sets. And the next approaches we are going here is trying to, let's say, use explainable AI so that we can trace back, for example, which part in the image is contributing to the information toxic or non-toxic, so that also via this way we can start transforming deep learning in something which creates knowledge and understanding. So these are our modeling approaches. And in the, let's say, second part of the talk, it will be a bit short as the first one. In the second part of the talk, I would like to introduce you to the second mainstream we are currently following in the group and also in Phenaris, and this is read-across. Read-across based on data, that's ToxPHACTS coming from OpenFacts. Markus already introduced the OpenFacts, the semantic data integration project we were coordinating, and from eTox, that was another IMI project where we tried together also with pharmaceutical companies and other colleagues from academia to predict the outcome, create models to predict the outcome from the 28-day rat tox study. So collecting data and trying to create models. So what we do in toxicological read across is we try to get a toxicity assessment based on similarity. So just assume that you don't have any data for compound 1, any toxicity data. You would like to get a first idea, of course, before you do the first animal experiments, to get a first idea what might be my safety risks. You look for similar compounds in the literature and in your in-house database where you have data. You see the structural similarity to thalidomide, contangan, and you immediately would be worried about, for example, developmental toxicity. So this is how read-across actually works. You try to assess safety based on similarity. The question is how you define, how you identify, how you use similarity. This could be not only one webinar, I guess that could be a symposium for 1 week, and we still maybe would not agree what's the best way. And I have the strong feeling there is not a best way. You need to tailor it for the distinct problem. So what is ToxPHACTS now doing? ToxPHACTS has 3 parts. It's doing similarity search. So trying to not just do chemical similarity, but maybe use a sort of different ways of similarity. It then queries, originally it queried the OpenFacts database. Now we currently query Campbell because it anyway was the main chemistry compound target interaction database we had in OpenFacts, and then you do the data analysis. What we do here is we analyze a compound target interaction profiles. So these are data then retrieved from Campbell. And if a target is related to toxicity, and this is a database we are running behind and we build up in Phenaris, if a target is related to toxicity, you get this flag and you can go a bit deeper. So let's go through the different steps about similarity. We just did a very basic analysis using benzodiazepines. And here you see if you use 5 different fingerprints, just looking into Campbell for the azepam and taking the top 50 ranked compounds. The good news is all of them are benzodiazepines. So regardless which of the 5 fingerprints you use, the bad news is you see the different similarity values and you see the different rankings of, for example, diclazepam in comparison to diazepam. It's getting even more striking when you take bromazepam, because this is the ranking, and you see you just make 3 more or less bioisosteric exchanges, and you get completely different rankings when you just use different fingerprints and screen camber. So what we need to consider and what we're currently doing is we just use different fingerprints and try to get a sort of a consensus in the hit list. What you see here is, again, our attempt going to the 3rd dimension. So here you see for sodium channel blockers, 100 conformations and also of descriptors. And you see that, for example, this compound here, flecainide, has its distinct chemical space when you do the PCA plot. But here you see, for example, when you look here, you have yellow, so propafenone, you have black N-kainide, and you have green warfarin. And you have them all together here. What does this mean? There are conformations which, on basis of Wolfsraf descriptors, 2 compounds are more similar to each other than to other conformations of the same compound. So this just shows when it comes to similarity, you need to be careful which algorithm you use when you target a certain problem. So how does ToxPHACTS work? Also here we offer 2 entries. When you go to toxfacts.univ.ac.at, you get the free version. And when you go to toxfacts.com or phenaris.com, you get the company version. The beginning is basically the same. You draw the structure and then you submit the query. In the free version, it's just max keys and we retrieve everything which is 80% similar. When you click on one of the compounds, then you are directly routed to Campbell, that you see where the information is coming from. No result in that case means that there are no biological data for this compound. Success means there are compound protein interaction data for this compound. We go down to 80% and we display the hit list. So what you see here is each line is a compound. When you hover over it, you see the chemical structure. You can also just blank it out. So each row is a compound, each column is a protein, and this is real interaction values. You can filter according to activity and make it just smaller. For example, as here, you can just blank out and check only those which are related to toxicity. So the different colors refer to different target families, as Diane Campbell, so membrane receptors, ion channels, transporters, transcription factors. And if you have a red spot, that means this target is related to toxicity. So you can here under sort targets, you can just sort it, getting those related to toxicity first or getting only those related to toxicity. You can increase the activity threshold to P IC50 values higher than 5, for example. You can scale the heat map. And then when you have cut it down and you click on it, here you see where the information is coming from. So you see that's COX-1, and you see it's considered to be an off target according to these publications, and what are the effects inhibition causes. And it's also considered to be related to developmental toxicity. And this is where we have the information from. So that's ToxPHACTS. What's the difference to the company version and the free version? In the company version, it's not just one similarity algorithm, it's 5 different similarity algorithms, and we do a consensus in displaying the hit list. And in the company version, you have this detailed information. In the free version, you just get the information. It's linked to DART and off target, and you get the literature, but you don't get more. So this is how we see data-driven read across. What is next on our agenda? Of course, combining. So combining the read across with predicted toxicity values. So our vision would be that you get a second block here. Here you have, this is based on data. There's no model behind. This is all based, the read across is based on data, and this is based on computer models on predictions. And of course, you could somehow combine it and get a more, let's say, complete picture on data-driven analysis and computational prediction. And that's, as promised on the beginning, at the end, I would like to show you. So I showed you how we deal with this compound protein interaction. I showed you somehow how we deal with this compound protein disease or toxicity. And now I would like to show you what our first attempts, how we link chemical structures to pathways. And for this, we use KNIME, and Barbara Pfütze in my group developed a quite complex KNIME workflow, which does the following. You take a compound, in that case, the chemical ID. You search in different databases like DrugBank, IUFAR, CANBO, for the first shell of interactors. So for protein interacting with this compound, then you take a protein-protein interaction database like Mentor and search for the second shell. So these are the proteins interacting with the proteins the compound is interacting with. And then you take all these proteins and map them to pathways. And then you just see if you have an enrichment of these proteins in certain pathways when you compare it to sort of if you would do that randomly. And what you get when you analyze, for example, all the withdrawn compounds which are in CAMBO, you see what are the pathways which are mainly hit by these compounds. So T cell activation, P53, apoptosis signaling pathway. So this is one information you get out of this sort of analysis. And the second information, what you get is a compound pathway interaction fingerprint. So each line is a compound, each column is a pathway. And then you can cluster according to these fingerprints, and you can start to analyze. And here you just, and we are currently building up a comprehensive database to really see why these compounds have been withdrawn, because that's not so trivial. When you just look on CAMBO, there are many reasons. Sometimes it's commercial or whatever. So to really find out why a compound has been withdrawn is an information which you need to check compound by compound. But here just we started with hepatotoxic and cardiotoxic compounds. And here you see these purple compounds. All of them have been withdrawn because of hepatotoxicity. There's not a single one which has been withdrawn with respect to cardiotoxicity. And when you look on this cluster, it's quite a distinct compound pathway interaction pattern. And in our vision, we see that we could maybe use that also as start predicting a sort of what could be potential reasons on a more complex basis. The drawback, of course, this needs a lot of data. We started with withdrawn drugs because if drugs, of course, have been measured across a lot of targets, and this information is in CAMBO. If you use that for a new compound, it might not work as long as you don't have the first shell of interaction fingerprints. But I guess in all pharmaceutical companies, you run the serep screens for your compounds. In that case, you have the first shell. And with the first shell of interactors, you can go into the workflow and you actually just start here to the interactome and then map on the pathways. So there is a way, even maybe not for the public domain, but there is a way for those having serep screens and having a set of panels of proteins tested for their compound to also implement this workflow. We have this KNIME, we have a KNIME workflow. And the paper, we currently write up the paper, and then the KNIME workflow, of course, will be made available to the public, start playing around. So this is our approaches we are currently using. I would really like to acknowledge my group. Mainly, Jennifer did a lot on the machine learning together with Ecker. Florentina did the mitochondrial toxicity stuff. Barbara did the compound pathway interaction fingerprints. Also Jana did a lot of workflows. Melanie is the CTO in Phenaris, and she is taking care that our commercial services are up and running And it's definitely a pleasure working with all these young people together currently remotely. All of us are on home office now, but I guess that will change in maybe 2 or 3 weeks. This is where the money is coming from, and I would like to thank you for listening, hopefully just being relaxed, sitting and listening and joining the webinar. Thank you very much.